Let's assume now that we want to go back from our sample signal to the original signal in CT. This process is called reconstruction, and we will first look at ideal reconstruction. For this, what we want to do is to extract the original spectrum of the signal x of omega. If we can perfectly extract the spectrum x of omega in the frequency domain, then in the time domain, the result has to be our original signal x of t. So in the frequency domain, what we want to do is to use an ideal low-pass filter with cutoff frequency omega s half, so that we can perfectly extract the original spectrum x of omega. For this, we have to multiply xs of omega with our ideal low-pass filter, which we call h of omega. Since our ideal low-pass filter h of omega is a rectangle in the frequency domain, the corresponding impulse response h of t is a sink in the time domain with zero crossings at multiples of ts. Since we have multiplied the spectrum of the sampled signal with the filter in the frequency domain, we now have to convolve the samples with the filter impulse response h of t in the time domain. So for each direct delta, which represents a sample, we get a shifted and scaled copy of h of t, which is the sink. All shifted and scaled sinks, where we have one sink for each sample, then form the original signal x of t. Since all sinks have a zero crossing at a given sample time, apart from the one sink that is centered around this sample time, this method guarantees that the reconstructed signal and the original signal are exactly identical for the sample instances. Also, if the original signal is band limited and was sampled without violating the sampling criterion, then the reconstructed signal and the original signal x of t will be exactly the same for all times. Unfortunately, this ideal reconstruction method can't be used in practice because h of t has infinite range between minus infinity and plus infinity. In order to perfectly reconstruct the signal x of t at a time between two sampling instances, all sinks have to be combined. Hence, in order to do ideal reconstruction, we have to know and take into account all samples of the past and all samples of the future. In practice, we use zero-order Holt reconstruction, where zero order means polynomial of zero order, which is just a constant, such that zero-order Holt means constant Holt. What it does is simply holding the output signal constant after receiving a signal until receiving the next sample, which is then also Holt constant. Mathematically, this can be expressed as a convolution of the sample signal with a rectangle of height 1 and width ts. To understand the possibilities and limitations of zero-order Holt reconstruction, let's go through the reconstruction process also in the frequency domain. The frequency response of the rectangle in the time domain is the sink function in the frequency domain, and since the rectangle has width ts in the time domain, the zero crossings of the sink in the frequency domain are at multiples of omega s. Then, the spectrum of the reconstructed signal is the multiplication of xs of omega and the sink function, since in the time domain the samples are convolved with a rectangle. So the result, the spectrum of the reconstructed signal, is close to our original spectrum x of omega, but not exactly the same. First, observe that instead of multiplying the spectrum with 1 for frequencies around 0, it's multiplied with the center of the sink, hence slightly distorting the low-frequency components. Also, the high-frequency components are not multiplied with 0 and hence cancelled out perfectly, but multiplied with other parts of the sink around the zero crossings of the sink. Hence, the high-frequency components are reduced, but not perfectly filtered out.